in this exercise, we want to show that each of these 1, 2, 3, 4, 5 limits are all equal to 0. Let's start with the first one. Limit as n tends to infinity of 1/3 raised to the power n. Remember that when we say n tends to infinity, it means n gets very, 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 very large. All right, this is the same as limit as n tends to infinity of 1 all over 3 to the n. Okay, so what we have done is we take 1 to the power n. Remember, 1 raised to any power is 1, and 3 raised to the power n. Now, this is simply when n gets very large, we're going to have 1 all over 3 to the infinity, which is even much larger. And so we'll have 1 all over infinity, which is 0. Anything divided by infinity is 0. Okay, so that's it for the first one. Now the second one, limit as n tends to infinity of n plus 1 all over n squared. Now, if we take the limit point here, infinity, and put it there for n, we're going to have infinity over infinity, which is indeterminate. So what we are all advised to do with such a case is that we take the higher power or the highest power of the variable n. The highest power of the variable n here is n squared. So we're going to divide each term in this expression by n squared to evaluate the limit. So we end up with limit as n tends to infinity of n all over n squared plus 1 all over n squared all over n squared all over n squared. Okay, that simply gives us limit as n tends to infinity of n all over n squared is 1 all over n plus 1 all over n squared, all of that divided by 1. Now, this we evaluate to as n gets very, very large. 1 all over infinity is 0. 1 all over infinity is 0. So we have 0 all over 1, which is 0. So this second limit also is 0. Look at the third one. Limit as n is going to infinity of n all over 2 to the power n. Now, here n gets very large. So the numerator will get to infinity and the denominator will get to infinity as well. 2 to the power n, as n gets very large, is also getting even larger faster. So in this case, the denominator is going to reach infinity faster than the numerator. And so we end up having a situation like a value at the numerator all over infinity. All right, and anything divided by infinity is 0. We should take note. Now, in the fourth exercise, limit as n going to infinity of a to the n all over n factorial. Again, the reasoning that we had in C applies here. If we look at this carefully, a to the n, as n gets very large, is going to get to infinity. Okay, our assumption here is that a is greater than 1. Okay, a is greater than 1. Here, a should be greater than 1. I'm sorry, I did not put that. So when that happens, a to the n will get to infinity, quite all right. But n factorial will get to infinity faster. So this one will get to infinity faster than that one. So that rational expression now will get to the same type of situation here where we will have a certain number all over infinity, which gives us 0. That is the reasoning. Okay. Now we look at the last one. Limit as x tends to 0 of ln x plus 1 minus x all over sine x. Now, we cannot apply the quotient limit theorem in this exercise because if we try to put the limit point 0 here, we're going to obtain limit as x approaches 0 of ln, that means we're putting x to be 0, of ln 1 minus 0 all over sine 0, which gives us 0 all over 0. 0 all over 0 is indeterminate. We cannot see anything there. So whenever we get indeterminacy 0 over 0 or infinity over infinity, after applying the limit points, we will have to take another method. It means we cannot get the solution using this quotient limit theorem. So we have to take the next method. The method could either be algebraic simplification or applying the L'Hopital rule. So the L'Hopital rule simply means we take the first derivative of the numerator separate, and then take the first derivative of the denominator separate, and then we evaluate the limit again at the point 0. So let's go ahead and use the L'Hopital's rule. So applying the quotient limit theorem, we have indeterminacy. Now let's apply the L'Hopital's rule. So the L'Hopital's rule says this limit will be the same as limit as x gets to 0. Getting to 0 means very, very small. We differentiate the numerator. Differentiating ln x plus 1 is simply 1 all over x plus 1. And differentiating negative x is negative 1 all over. Differentiating sin x gives us cos x. So this is the limit. This is a new limit when applying the L'Hopital's rule. Now, let us see if we put 0, if we put 0 in the place of x, we're going to obtain a result. If we put 0 in place of x, here we're going to have 1 all over 1, because this will be 0, 1 all over 1, which is 1, minus 1 all over cos 0 is 1. So we obtain 0 all over 1, which is 0. So it now confirms that all of these limits actually are all 0.